Okay, so in this video, we're going to talk about scientific notation. Okay, so scientific notation is used to write very small or very large numbers. So we use it to shorten it, I should say. We use it to shorten very small or very large numbers. And by very small, I mean if you're talking about um, something like something under a microscope or something like that, you had to measure how small it was. It would be a very, very, very small number. So it'd be a number with a decimal and a lot of zeros. And so, or in the case of large numbers, if you were to add up the amount of money Bill Gates had, right, that's a very large number. And so scientific notation gives us the opportunity to shorten those numbers and make it easier to read, right? And so scientific notation uses powers of 10, which you should have watched the video on already, to shorten the length of a number. So if it's a very long number, whether it be very, very large or very small, if it's a long number, then we can use scientific notation to shorten it. So here's an example. If I have 1,200,000, I'd be able to use scientific notation to shorten that number. What I would do is I would say, well, the decimal is at the end of this number here, right? I would just move the decimal over 1, 2, 3, 4, 5, 6. And I would be able to say that this is expressed as 1.2 times 10 to the power of 6. So that would be our scientific notation. Let me zoom in on it. So that would be the scientific notation for that number. For 1,200,000, the scientific notation is 1.2 times 10 to the 6th. And so again, it's just taking large numbers and making them more manageable to look at, right? And so on this scientific notation here, we have certain parts of the number. Okay, so this number here in the front, that's the number we use. That's a shortened version of the number we use. That's called the coefficient. It's COEFFICIENT. Again, it's COEFFICIENT. So I messed up and I had to put the I in there. I wasn't going to redo the whole thing. So again, the COEFFICIENT, right? So that's the coefficient. And then we have the base number here. The base number is always 10. It's always times 10 to the something power, right? So it's going to be 1.2 times 10 to the 6th power. This to the power of, that's called an exponent. So we have the base of 10, and then we have our exponent of 6. And so the coefficient must always be greater than 1, but less than the number 10. So it must be always greater than 1, but less than 10. So this number here, this 1.2, it had to be greater than 1, which it is, it's 1.2, and it had to be less than 10. The base, as I stated before, the base, I'm trying to zoom out here. The base is always 10. So we have 10 here. The base is always 10. So if it's scientific notation, it'll be some number times 10 to some kind of power. But the base is always 10. It never changes. And then here we have the exponent is the number of spaces the decimal was moved to obtain the coefficient. So when we came up here to get to that 1.2, the coefficient, we had to move the decimal 1, 2, 3, 4, 5, 6 times. And so 6 became our exponent because it lets us know how many spaces we need to move back to get back to our original number. So the exponent is the number of spaces we moved to obtain whatever our coefficient was. Okay, and so a negative, exponent means we move to the left. A positive exponent means we move to the right. So here we have, and what I mean by that is, if I wanted to take this 1.2 and make it 1,200,000 again, then I would just move 6 spaces to the right. So it would look like this: 1.2, right? I would move 1, 2, 3, 4, 5, 6 spaces to the right, and I would fill in these empty spaces with zeros, and I would again be back to my original number of 1,200,000. So the exponent tells us exactly how many spaces we move to obtain the coefficient, and if it's negative, that lets us know that we move to the left to get back to our original number, and if it's positive, that lets us know to move to the right to get back to our original number. Okay.